Hello, I'm Jonathan Graham. I'm a senior system engineering undergraduate at George Mason University. I will be doing a quick little overview of our senior capstone project, which is the design of a single pilot cockpit for airline operations. My teammates were Chris Hopkins, Andrew Luber, and Soham Trivedi. So start off with some context. Our scope that we're looking at for this research is large commercial air transportation, which we take Bureau of Transportation Statistics, how they define that is carriers that have more than $20 million in operating revenue, and domestic operations, so it's the U.S. airspace, and we inflation adjust all of our dollar figures to 2012 dollars. So this graph here shows our profit and loss for major carriers. Notice that up until about 2000, they were somewhat profitable, and then there's this period of bankruptcies and really up and down in profit and loss and net income. So overall, pretty unstable during this most recent period. And when you look at the operating expense, it's steadily rising here over the period 1990 to 2012, and then projected to keep going. And of that operating expense, fuel really was the driver over the last decade. And we're saying, or for our purposes, we're saying that fuel costs are definitely more challenging to control than something like labor. So we are going to focus on labor. And pilot labor, though steady, was still a pretty large portion of that $100 billion or so operating expense. In addition to that cost figure is the fact that, according to FAA and some other reporting, there's an expected pilot shortage in this commercial area. So you're having cost issues, and you also might have a pilot shortage, so that drives kind of looking at a single pilot cockpit. Now on this slide, an interesting historical note is going to demonstrate here is the historical evolution. So on the left, you start with 5 pilots, and then over time, certain technologies eliminate the need for a pilot. So the radio operator goes, and then the navigator, the flight engineer, and now we're going to say, can we get rid of a co-pilot? Is there some technology, or is the safety of the aircraft good enough, or whatever the case is, where you can have a single pilot? So our focus is going to be on the flight deck, and we isolate the 2 roles of these 2 pilots, where you have a pilot flying and a pilot not flying, also as a captain and a co-pilot. Though pilot flying and pilot not flying are interchangeable, they're not static. And in general, due to flight requirements for certification by the FAA, you have to really balance these 2 roles between the co-pilot and captain. Otherwise, no one would ever really get trained. Also to note, yes, there are more than 2 pilots in certain aircraft. Usually, we're going to say that that's the international flights, the larger planes where you actually have to have a rotating crew. That's out of our scope. Again, we're in the U.S. airspace. Looking at some of the cockpit avionics that are common, these are some of the technologies that eliminate the need for certain pilots. And what's governing these pilots in the cockpit are the flight procedures. For our purposes, we were able to obtain a BAE RJ100 flight crew operating manual, which dictates or has a section that tells all the standard operating procedures that a pilot flying and a pilot not flying are supposed to do. And for our analysis, we're going to look at how workload is affected whenever these procedures change under different system designs. So a procedure, as defined in that operating manual, is broken up into 63 different distinct procedures, and those are normal and abnormal procedures, which are then decomposed into 613 tasks, which we decompose further into specific actions, which characterize physical and mental actions that are required to accomplish that hierarchy of procedure tasks. As an example procedure, here's an activity diagram, or sequence diagram, sorry, where you have a pilot flying, the pilot not flying, the actual aircraft, so that would be really the cockpit part, and an air traffic control block. So the pilot flying, this is a wind shear detection procedure, by the way. The pilot flying starts by doing some physical instrument manipulation where he's pulling levers and pushing buttons. And then he does a verbal cockpit call out to the pilot not flying, who then is initiated to do more physical instrument manipulations with the aircraft, Cockpit Avionics, and then does a final report to ATC. So these terms I'm using, the instrument manipulation, cockpit call out, these are kind of our ontology that was developed to characterize these actions, so the lowest level interaction in the cockpit for our purposes. So going on in the stakeholder analysis, we've kind of grouped some of these various high-level stakeholder groups. So you have regulatory agencies like the FAA, the aviation workforce, so pilot unions, air traffic control, their unions, the customer base, and then the aviation industry as a whole. So air carriers, the management of those air carriers, or airliners, if you will, manufacturers of the aircraft, insurance, airports, etc. And this nice graphic here to kind of describe some of those tensions that you have. So regulatory agencies would be pretty hesitant to transition such a large overhaul in the air system to go from these 2-3 pilot cockpits down to 1. And then pilots, of course, would be a little miffed at first because you might have issues with perceived job threats, things like that. But again, there's a pilot shortage, so there might be win-win there. Pilot unions, ALPA, the air traffic controllers, and their unions. Again, these kind of labor groups resistant to change. Your commercial air carriers, airline management, and your aviation industry overall might be willing to support something like a single pilot cockpit due to the potential market benefits for reduced cost, increased sales for planes, things of that nature. Of course, there is a risk profile associated with that, so you got to get regulatory and of course insurance companies, things like that on board too. So a lot of tensions going on, but you know, will be addressed later with a win-win. So into the classic problem need here. The problem, we have rising operating expense and overall financial instability. Profitability has been difficult to achieve, and we have a pilot labor shortage. So a notional gap here, we look at the operating revenue and operating expense. Back whenever there was profit in the industry, or more consistent profit between 1990 and 2000, you had this ratio above 1. And you know, it's basically common sense. If you bring in more money than you spend, then presumably you'll have a profit. And if you look past 2000, you've been below 1 or just at 1. So our gap is trying to raise that ratio. So if you can decrease your cost and then allocate that somewhere else to increase revenue, then you can start driving to more profitable industry. So the airlines will continue to have volatile financial performance, and operating costs will just keep growing here. Fuel largely being the driver, but labor expense can be controlled a little better. Single pilot cockpit is needed to decrease the labor expense and mitigate the effect of a pilot shortage. So there's a lot ahead of you with trying to satisfy all these different stakeholders, and a win-win could possibly be the actual phase in of this technology versus just like a light switch. You go from 2 to 1. So notionally here we have a 2-pilot cockpit as we have today, and then within 5 years you have some sort of 2-pilot cockpit with your alternative. So you keep those 2 pilots there to evaluate it, and you keep evaluating, testing, refining, so very iterative, and then you eventually transition to a single pilot cockpit. So this gives you a lot of time to analyze and kind of satisfy a lot of these issues that these stakeholders would have. Some high-level mission requirements we've developed were for the procedure time, so we're going to put a boundary on their baseline procedure time. Reliability requirements and costs, so you're concerned about safety, and then these values come from our analysis, which will be described further later. So into the design alternatives, first we'll start with the physical process diagram. This is kind of where we branch our design alternatives from. And we start with operating procedures, which have pilots that are kind of triggering these, or not triggering, these are mechanisms for the triggered flight goal and air traffic control. So they're receiving commands and they're trying to hit a target goal, and they're selecting these procedures and implementing them within the cockpit, which are your avionics, and then they're issuing aircraft control to the actual aircraft. And you obtain your outcome, or you have that feedback loop with that aircraft dynamics, and you just keep doing this. So again, it's a kind of a steady state here. In our design alternatives, we'll basic 2-pilot, so this is the no change option. We just keep everything the way it is. Single pilot with no support, so it's just a lone guy flying. That's a picture of a U-2 cockpit, so very common in the military, but we'd be trying to do this for commercial. And then a single pilot with onboard support system, so that is that single pilot who's flying, but he has some sort of avionics hardware. Black box at this level, but it's there and it has some basic functionality that can handle some of the workload that the co-pilot would have, or the pilot not flying would have. So how do we analyze all this? First, we'll look at the three different, or the really high level overview here. We started with a procedure simulation, which we start with that FCOM that was in the context, codified into Excel, converted into XML schema, which is actually served as the model input, or the input for the simulation. And there's three different models that were generated for each alternative. So one for the two pilot, which is basically the manual. And then there were some rules of thumb developed to change how we eliminated some of the procedures for the single pilot case and the single pilot with onboard support system. And that gets pumped into a Java simulation program, which underneath has that has a model human processor, which is a queue network of different processing nodes that basically those actions all the way at the lowest level of our model get processed through, which I'll explain more in detail later there. But below that, we have a reliability modeling, which we start with reliability block diagrams and see what happens to the actual safety in the cockpit whenever you start changing the serial and parallel configuration of the cockpit with the aircraft. So what happens when you remove a pilot, or if you have a system that can take over for a pilot, things like that. And those two inputs get combined into a utility, which will use a lifecycle cost model to develop the savings potential for the alternatives, and then eventually drive for a recommendation. So start with the procedure simulation, a lot of assumptions here. We start with the human model processor. This is going to approximate our actions in the cockpit under normal flight conditions. So this is best case scenario, no pilot that's fatigued, or he has something on his mind, or whatever, he's optimal condition. The events are independent of each other, so they're not related in any way. If there's an issue with one, it's not going to carry over to the other. Normal flight conditions and expert skill level. Presumably pilots have to be experts to fly at a commercial level. They have a lot of flight experience and they have to be certified. So and we assume the alternatives follow contemporary avionics costs. So for that onboard support system, it's not going to be absorbently expensive. It should be relative to a similar system that does similar functionality, or not functionality, but complexity. The RJ100 is representative of similar operating manuals. Of course, not all of them are the same. If you have a 737 or 757, they're going to be different, but we're going to say that this approximates most of them. And the procedures in these manual are complete representation of normal or of flight. Additional company-specific pilot tasks, which are very common, are not included in the manual, and therefore are included in the analysis. So for inputs, again, kind of driving the point home, we started with that standardized operating manual and then broke it down into this XML model, which gets parsed into the simulation and is processed according to the model human processor, which is a network that breaks up into, or a high-level network broken into perception, cognition, and motor, with a lot of pieces below that, sub-network pieces that kind of make up some of the ins and outs of each of those higher level. So grounded in a lot of human factors research. So if you're familiar with this area, like ACTAR, GOMS, Fitzlaw, a lot of these pieces are kind of placed up in there. And we add our own block for a processing time for avionics. And this is just kind of a little mini animation. So over on the left, you have that tree. That would be the XML. And an action comes in and gets processed by the perception, and then goes through cognition, and then hits the motor if applicable. So for instance, if he's playing with an instrument. And these get summed up, and you'll get an actual processing time for that action, which then those sum of actions get summed up to the sum of tasks, which eventually you'll get an actual procedure time. And these are the equations that are used, so some of various distributions for various sub-network nodes. And then these are just summed up in a Monte Carlo-like fashion, and you'll get a processing time for each procedure, And for analysis, we're going to look at if there is a difference, statistical difference in our two-pilot case, and then what's the workload. So workload is a ratio for the procedure, so discrete individual procedure time compared to the two-pilot procedure time. So if it's greater than 1, then it took more time for another pilot to fly than the two-pilot to fly. In the design of experiment, we have our input, which again are those 3 different models which have different tasks. They're manipulated based on the capabilities of each design alternative. We add an additional processing node for the onboard support system, and then our output will be workload and processing time. Queuing over to reliability modeling, we looked at what is the safety, baseline safety in the airspace system now. NTSB puts out some data, and based on that, there's about 2.2 accidents a year on average from 1993 to 2012 time period, with an average of 14 million or so flight hours a year. And we treat that as a failure rate, so 2.2 on average, 2.2 divided by 14, and you'll get your failure rate, and then we'll convert that to a per hour basis, and then use that in reliability block diagrams to see what happens for basically your space of allowable failure. So what can you certify to meet a certain reliability requirement, which I might have skipped over in the previous slide, but at 1 million flight hours, which we fix in our analysis, is 0.8674. So there's a 86% chance you can continue flying at 1 million flight hours without actually having an accident in the airspace system. And a major accident is defined as a loss of life or a catastrophic loss of the aircraft hull. So on the left-hand side, you have a two-pilot cockpit, and parallel, you have a pilot and a co-pilot. If one is incapacitated, the other can continue to fly the aircraft. And the aircraft is, of course, whatever its piece is in serial with that cockpit. The single pilot, though, if he goes, then it all goes. So it's a serial reliability. The onboard support system, we're going to say that it has a functionality or capability where it can actually support a pilot incapacitation event where there's either a ground trigger or another person on the plane can trigger an emergency auto land or auto transition effect. Again, really high level assumption, but we don't think it's out of the scope of possibility given the current UAS capability with a lot of the military hardware and even civilian hardware at this point. So design of experiment, we basically varied the failure rates from 1 in 100,000 to 1 in 10 million hours. You have a catastrophic failure in one of these components, and then see where you have to be to meet that 0.8674 system reliability and system retreating as the airspace system. So we're not talking to individual aircraft here, we're talking over your entire system. What are you dealing with? And then the output, those are your output equations. In the business case, we developed a life cycle cost model for 25 years. We looked at data for 737 out of Form 41 filings from the Department of Transportation, and used the average pilot labor cost, and so basically a starting acquisition, a salvage at 25% of the acquisition, which really isn't too important because we're really looking at the pilot labor and what happens when you remove a pilot. So what is your life cycle savings? So you have a life cycle cost, and then you have a net savings. So the savings would be the difference between the two-pilot case and then the one-pilot case. And basically whatever you save over that life cycle, you'll have to invest in other areas or into that other alternative, the onboard support system, on a per aircraft basis. And then we include an escalation term because presumably supply and demand, if you have a shortage of pilots, you'll have an increase in the cost for pilots. So that's in there to see, give you some range, given a barrier rate and given an escalation rate. What are you looking at in terms of cost savings? And then here's the design of experiment. What we vary, and we'll go in more detail in the results section. A value hierarchy was generated, so our outputs populate this from each analysis. That's in red. Blue would be ideally where you would look at going forward, but for now, red is what's in scope. In the results, so in the procedure simulation, this is just a sample here in that graphic of the procedure times, the average procedure times, just a small little sample for 10 different procedures. The two pilot obviously had longer times because there was more interaction. The cockpit took longer to, or more actions to complete before you could complete a procedure. Single pilot had less because you're actually eliminating a lot of the time with interacting with another pilot and kind of the back and forth there. And the pilot support was kind of close in most cases, but usually came in second with regard to least time, double most time. But both had a significant difference. P basically 0. And the takeaway is the time the pilot spends performing tasks decreases because as predicted, you would eliminate tasks from that procedure tree, then you'll have less time. No distributions can be fitted to the this is a histogram here of the procedure times, but there's some population parameter or sample statistics there, so you mean median standard deviation. As for the workload for single pilot was significantly higher, about 4.17, compared to the onboard support system had actually reduced workload per our analysis. So the takeaway here is that so the takeaway here is that you have an increased workload on the single pilot. So he's working faster, but he's working harder. So there's some implications there where you might have issues with error rate might peak and his exhaustion might start going up. So a lot of human factors implications there, which would require further analysis with live subjects. When the reliability we looked at, you'd have to have one failure in every 23 million flight hours for the single pilot case, which doesn't really work with the current flight safety, so we deem that as infeasible. If you can certify your avionics to a reasonable, million plus one in a million plus failure rate, then you should be good when you have a pilot flying with it. So we judge that as being feasible. The single pilot savings, or best case, you'd have $4.38 million per aircraft, which you could invest or allocate otherwhere or to other areas. And worst case, you would have 100K. So that's really a business decision. This should be extended further on a per airline basis, and you can add in more deeper research, such as maybe efficiencies in fuel or maintenance, things like that. But for now, this is just high level, best, worst. Not too bad. Utility we looked at, instead of going in and doing surveys and things like that, just looking at starting with sensitivity analysis, where if you max each attribute, where do you end up for the alternatives? And really you never do well with the single pilot unless you look at procedure time, which even then it's marginally better in terms of value there. So for the most part, you're going to win with the two pilot and the single pilot with onboard support, and the onboard support would potentially have savings. So we'll get into that with recommendations. So with requirements that we had at the beginning, we satisfy them with the onboard support system, and we don't with the single because of the safety implications, the reliability. For a recommendation, our utility ranking, we have the two pilot, then the single pilot onboard, and single pilot. The single pilot has cost reductions, but the workload safety bounds overall the utility there, and the safety mechanism for pilot would give alternative increased utility if you actually add that in, which is basically our onboard support system. So we would recommend to actually implement or go forward with using the single pilot with an onboard support system. And here comes back that win-win. If you can evolve that design and integration in over that win-win period, it could be a success for regulatory body, consumer, labor, all those stakeholders. So of course, this is very infant research, and it'd be good to actually tie this into a live simulator and see a lot of those human factor implications, and kind of work this over with stakeholders and things like that and see what they actually think about the idea of flying with one pilot, and start actually working on an onboard support design, so not just treating it as a black box, but design a requirements baseline that you can flow down and start designing hardware and seeing if you can realize cost savings or do some of these assumed failover capabilities. And thank you.